now.
Okay, so hi everyone. Thanks for coming to this week's AFMS seminar. It's my pleasure to introduce our speaker for today, Cristian Marchioli, who's an associate professor of fluid mechanics at the University of Udine. His research interests include multi-phase flow modelling from small-scale particle turbulence interactions to large-scale modelling of gas, solid and gas liquid flows, and is going to be talking about some of that work today. So please take it ahead, Cristian.
Okay, thank you very much. I don't think you can see my camera anymore, right? So it's just the slides.
I think if people have the camera open, they'll be able to see you.
Okay, they will be able to see me. Okay, okay.
That's right.
All right. So thanks a lot for the kind introduction and for inviting me, and for those who are here, thanks for being here. And if you woke up very early, for being here, thanks also for that. Now, in today's talk, I would like to make a sort of overview of the activities that we have been doing at the University of Udine over the years concerning the simulation of turbulent dispersed flows. So flows in which a dispersed phase, typically solid particles, is brought about by turbulence. And in particular, we have been working a lot with the point particle approach. So we are interested in particles that are, let's say, small, and I will come back to this later on, and can be treated as material points moving inside the fluid. Now, this is, of course, a strong simplification in some cases, less strong in some other cases. But I think that even with these simplifications, we can learn a lot from the point of view of the physics of particle interaction with turbulence. So I would like to give you a sort of overview of what we have been doing and learning over the years. Now, the results I will show you come from different projects, so to say, and different activities that have involved a lot of people. And in particular today, the results that I'm going to discuss with you have been obtained together with two PhD students, Diego Dotto and Arash Sharifi, and of course with Professor Alfredo Soldati, who used to be the head of the fluid mechanics group in Udine, and now he is in Vienna at the Technical University in Vienna, and we are still, of course, collaborating in that. Okay, let's see if, okay, it moves on like that. So this is a short outline of the talk. I'll try to keep the time. And I divided the talk into three parts. The first one is related to particle turbulence interactions when inertia, in particular the inertia of the particles, is the driving player. And as I mentioned, I will start by focusing on small, spherical, and heavy particles in turbulence, and tell you a little bit about the physics that we think we have learned from the adoption of an Euler-Lagrange approach that is based on direct numerical simulation of turbulence. Then in part two, I will sort of complicate a little bit the problem and talk about what happens when inertia is not the only reason or the only player, as I write here, that governs particle turbulence interaction. So in this case, I'm going to add additional variables, let's say, to the problem. And in particular, I will overview the case of non-spherical and deformable particles, which I will refer to as flexible fibers, and see how the changing shape and the deformability adds to the effect of inertia. And in the last part, I would like to tell you a little bit about what happens when you add a third phase to the problem. So in particular, in this case, the third phase is represented by deformable, large deformable drops, which are also brought about by turbulence and can interact with our small particles. And I will talk a little bit about the processes of capture and trapping of particles at the surface of the drop. Okay, so let's start from part one, physics of inertia-driven particle turbulence interactions. And I would like to start by showing you this picture, which you probably know. That's a very well-known result for those who work on dispersed flows. And I would like to draw your attention to this picture here. Summer is almost over, but perhaps this picture reminds you of, the bottom of a swimming pool in a nice summer day. Unfortunately, it's not like that. This is a snapshot taken from a direct numerical simulation of homogeneous isotropic turbulence. So in this case, the computational domain is a cube that is not bounded by walls, within which you have a turbulent flow. And this is just a 2D snapshot taken from this flow in which small particles have been added. Now, in a turbulent flow, we know that there is a wide range of space and time scales, and the smallest scales are the Kolmogorov ones. In this case, the particles that are injected into the flow are much smaller or significantly smaller than the Kolmogorov scale. This allows what I will present later, so the treatment of particles as points. But anyway, the situation that we have here is that of very heavy particles compared to the fluid. And if you let the particles evolve in the turbulent flow, after some time, you will see that they attain a non-homogeneous distribution, which is represented here by the snapshot. So where you see these yellow or greenish regions, that means that you have a very high concentration of particles, what I call here number density. And these regions are alternated by these blue regions, which are almost empty of particles. So no matter what is the initial condition with which you start your simulation, after some time, you will get these non-homogeneous distribution of the particles. Now, the only reason that drives this non-uniform distribution is particle inertia. In this case, inertia is related to the very high density ratio. Now, there can be different mechanisms that lead to this preferential concentration in some regions of the flow. In the literature, you can find, for instance, a sort of centrifugal mechanism. When this mechanism dominates, particles will concentrate in high strain and low vorticity regions. But another mechanism, the sweepstick mechanism, has been identified. And when this mechanism is dominating, then the particles will concentrate preferentially in low acceleration regions. But the point I want to bring out here is that no matter what is the mechanism, the underlying mechanism, you will find this macroscopic particle behavior. Now, you can complicate a little bit the flow and, for instance, bound it by walls. So you can make a direct numerical simulation of turbulence in a channel, for instance, which is a very standard geometry. And in this case, what you see here is an animation of a turbulent channel flow laden again with particles that have a size smaller than the Kolmogorov length scale. And what you see here is the evolution of these particles, so the dots. And in the background, you can see the distribution of the streamwise fluid velocity. So the flow is coming towards you in this case. And that's the geometry that we are considering. And this is the section that we are looking at. Now, in this case, the flow, of course, is a bit more complicated than before because it is bounded by walls. So the wall normal direction is now non-isotropic and non-homogeneous, all right? So as you can see, we choose an initial condition for our particles. They are uniformly distributed, but after some time, you maybe recognize the same non-uniform spatial distribution, both in the center of the channel, but perhaps you are also able to see here regions which are more densely populated by these dots. So these are the particles. And indeed, we can see, and this is also very well known result in the literature, that these particles tend to accumulate close to the walls. This fact is quantified in this plot on the left, where we show the particle concentration. So this is nothing but the number of particles per unit volume. So it's a number density distribution, if you want, as a function of the wall normal coordinate, which I call Z. I'm using this convention that Z is the wall normal coordinate, not Y plus. So I apologize if you are used to a different notation in this case. But anyway, the curves that you see here represent the concentration of particle along the wall normal direction for different inertia of the particles, which is parameterized by the Stokes number, which I will define in a more formal way in a few slides. But for the time being, it is enough to say that the Stokes number is proportional to the inertia of the particles. So you see that if I increase inertia, there is a clear increase of concentration close to the wall. In this plot here, the wall normal coordinate is represented in wall units, and therefore the viscous sublayer in this flow is within 5 wall units from the wall. So 5 is more or less in this region here, so you see that the peak is clearly inside the viscous sublayer. So that means very, very close to the wall. And the effect of inertia is obvious, so it enhances wall accumulation, all right? So these are different values taken from an old direct numerical simulation that we did. Now, without entering too much into detail, we see that there seems to be a common macroscopic features that can be identified for particle behavior in the turbulent flow. Now, what is determining this macroscopic behavior more or less in all these kind of flows? I could have made more examples, for instance, a particle-laden turbulent jet, and we would have observed the same type of behavior. Well, the simple answer is that in all these flows, particles do not follow precisely the fluid streamlines, but rather deviate from them. In the examples that I've shown you so far, the only source of bias is particle inertia, all right? And the effect of particle inertia can be quantified, as I sort of hinted to, by the particle Stokes number, which is usually defined as the ratio of the particle relaxation time and some characteristic time scale of the flow. So this particle relaxation time is the time it takes for the particle to adapt to any perturbation induced into its motion by the underlying turbulent flow. So what is known is that depending on the Stokes number, we can have a different kind of interaction between particles and the turbulent structures that occur within the flow. In particular, if the Stokes number is very small, ideally going to 0, then our particles have 0 inertia, so they behave more or less as fluid tracers, and they can follow the streamlines very neatly. In this case, one would not observe the non-uniform distribution in space that I told you before. So particles would remain uniformly distributed because they would behave, let me say, like an incompressible phase. If the Stokes number is very large, let's say much larger than 1, then particles have a very high inertia. It takes a lot of time for them to be able to respond to the underlying flow, and they will sort of ignore the structures. They will follow their own trajectory in a sort of ballistic way, And eventually, what you would see in the flow is, again, a sort of uniform distribution, but for a totally opposite reason with respect to tracers. The case that we are interested in is when the Stokes number has a finite value, let's say order 1, if the flow time scale is equal to the Kolmogorov time scale, because in this case, there will be a preferential sampling of the trajectory. So there will be a deviation driven by the Stokes number. Now, knowing this, we can think of starting with the simplest case possible, with the simplest approach possible, in order to study preferential concentration in the simple situation in which inertia is the only player. Now, the simplest case is, as I sort of told you already, the case of small particles, so smaller than Kolmogorov, spherical, so the shape is the simplest possible with no geometrical discontinuity, and therefore particles can be treated as points moving within the flow. This is the simplest dynamical model, because if we can stick to these assumptions, then we have that our particles do not create any wake in the flow, so it's a sort of Stokes flow, and the Reynolds number of the particle defined as the product of the relative velocity between the particle and the fluid, some characteristic length of the flow, and in this case it would be actually the particle size divided by the viscosity of the fluid, is much smaller than 1, again ideally 0. Because the size of the particle, d is the diameter, is much smaller than the Kolmogorov length scale, it will also be much smaller than the grid size, in particular if one is adopting a direct numerical simulation approach. And for this case, we can integrate well-known equations of motion for the particles, so for the particle trajectory xp and for the particle velocity vp. In particular, to know the time evolution of the particle velocity, we can solve for a force balance in which the inertia of the particle, which is on the left-hand side here, is balanced by the summation of the forces which are acting on the particle and are determining its trajectory. These are several, let's say, but again, if we consider the case of particles that are much heavier than the fluid, then the main force is the drag force. And for this force, we have very well validated models. So let's say we can be very confident that our equations are accurate and represent the physics of this simple situation that we have been considering. Now, the bottom line of this is that using this dynamical model, it is enough to know the trajectory and the velocity of the particle to be able to know everything about the particle. And for instance, the physics that we can learn can be understood using an Eulerian Lagrangian approach, as we did. So this slide is just meant to tell you that our approach solves for the Navier-Stokes equation for turbulence using direct numerical simulation of these equations, coupled with this Lagrangian particle tracking, which I just presented to you. Now, another important point is that the results that I will show you refer to a case in which the dispersed flow is in the dilute regime. So the particle mass fraction and volume fraction are always considered to be low, right? In this case, if again we can stick to this limit, we can neglect the effect of the particles on turbulence, and we can concentrate on the fact that turbulence have on particle dispersion. So I will refer mostly to results obtained in the one-way coupling regime. So again, only the effect of turbulence on particles is taken care of, and the feedback of particles on turbulence is for the time being neglected. And clearly we can focus a lot on the simplest case of spherical particles, but we also did some simulation with rigid fibers, so something, let's say, of these kind of shapes, so a prolate helipsoid rather than a simple sphere. But in general, I will focus on non-spherical particle effects later on. So what can we learn? What can we learn using this very simple approach? This is one example that refers to the same turbulent channel flow as before. So this is a snapshot in which you can see the instantaneous distribution of the particles. And this is a close-up view of a near wall accumulation region, this one here. Now, there are several things in this close-up which I need to describe. First of all, the circles, the colored circles are the particles. The ones that are in light blue here, for instance, are particles that are moving away from the wall. So these are colored based on their normal velocity. Whereas the purple particles that you see at the sides are moving to the wall. On the background, you see the color map of the streamwise fluid velocity. So again, the flow is coming towards you. And in red, you have high streamwise velocity. And in blue, which is partially hidden, you have low streamwise fluid velocity. Then perhaps you can see also some vectors. This is the fluid velocity in the plane, in the cross-sectional plane that we are visualizing. And I would like to draw your attention to this region here, so just at the sides of the blue particles, because in this region, you can perhaps notice that the arrows are identified as sort of local recirculation. This is actually the footprint of two vortices which are populating the near wall region. And you can see that the motion of fluid, which is induced by these two vortices, is also responsible for the transport of particles in the wall normal direction. So in particular, in between the vortices, particles are ejected away from the wall. They are actually entrained in an ejection of fluid, which is moving towards the core of the flow. And at the sides, the particles are driven towards the wall. So this shows clearly that the macroscopic distribution of particles is just the result of a microscopic interaction between the particles and the structures of the turbulent flow at the particle scale. And this is just one example, right? And by elaborating on these qualitative results, for instance, we can show that the preferential concentration that I told you before and the accumulation at the wall that we observe in a channel is actually a sequence of steps. So first, we need to be able to reproduce as accurately as possible all the structures within our turbulent flow, because in that case, particles will be able to interact with all these structures. The interaction will lead to segregation, that means preferential concentration. And if the flow is bounded, this will also lead to accumulation at the wall and eventually deposition. Now, this was for small, spherical, heavy particles. So only inertia is what I call here source of bias, meaning that only inertia is causing deviation from the streamlines. But in many cases, of course, particles are non-spherical. They are not rigid, so they can deform under the action of turbulence. And well, for some cases which I will not cover, they can also be active within the flow rather than passive. So they can propel and move independently inside the flow, even if the fluid is at rest. Now, so that of course makes the situation more complex, because particles are also anisotropic in this case, and this anisotropy adds to that of turbulence. That implies that if we want to still use the dynamical approach and model that I presented, well, we need to introduce additional functionalities in it. Because if we have a small sphere, it is enough to know trajectory and velocity. as a function of time, but well, for some applications, we might be interested also in rotation of the particle. So we need also to investigate the rotational dynamics, and we need an equation for it. If the particle is non-spherical, for instance, let's assume that this non-sphericity can be represented by just the aspect ratio lambda of the particle, then we need to know all these quantities as a function of the aspect ratio too. There will be an influence. In case the particle is non-spherical and maybe also active, so it can move within the flow, well, we must know also the time behavior of the orientation, which is indicated by this vector P. So P represents the instantaneous orientation of the particle inside the flow. And if the particle is deformable, then we need additional constraints for the particles. So in general, we need to make our model more and more complex. Now, let's see then what happens if we do that. So if we complicate the situation. So what happens when inertia is not the only player that determines particle interaction and distribution within turbulence. Now, I would like to show you one case which we investigated a few years ago, not too many, and this is the work of Diego Dotto. So this is the dispersion of small flexible fibers in a turbulent channel flow. So in this case, fibers are still inertial because they are heavier than the fluid, but they are also non-spherical and flexible, meaning that they can deform under the action of turbulence. And we wanted to investigate the process of particle dispersion and preferential concentration and wall accumulation in the presence of these additional sources of bias. Well, the first motivation came from pulp and paper making, because you see here that cellulose fibers that are used for paper and pulp and paper production are clearly non-uniform. But I would say that the type of fibers that we have investigated are closer to environmental applications. And the reason for investigating this problem was also related to some methodological aspects, because at that time, what people did was either to simulate and consider simple rigid fibers, so not deformable, in complex turbulent flow, like a turbulent channel, or complex flexible fibers in simple shear flow. And here I'm showing you some examples in which the flow is 2D or just characterized by a linear shear. So let's say what was missing was the complexity of a flexible fiber coupled with the complexity of the turbulent wall-bounded flow. So we decided to tackle this problem, and from the modeling point of view, what we did was to build our flexible fiber as a chain of small segments. It could have been also spheres, which are connected by ball and socket joints. So this is the so-called bead model that has been applied many times in the literature. So here I'm just providing, let's say, some reference papers in which this method has been applied for the first time. So the main point here is that we can decompose, let's say, our fiber in many small segments, or as I said, spheres, and for each of these segments, we can solve for the Euler's first and second law. So this is exactly the equation that I showed you before, the force balance, in which, in addition to the drag force, which is acting on the individual element of the fiber, we need to take into account, of course, the constraint forces, which I indicate here as X, which are induced on our element by the neighboring ones through the constraints, all right? And of course, as I mentioned, we need also an equation for the rotation of each of these elements. In addition, we don't want our elements to detach. They must stay attached to each other, and therefore we need to impose also some connectivity constraints. Now, I put all the equations here, but I don't want to enter too much into detail. If you're interested, I can discuss them later on. But the main point here is that we can generate, by using this bead model, a fiber that is longer than the Kolmogorov length scale in the flow, as a chain of segments which are smaller than the Kolmogorov scale. And because each element is smaller than Kolmogorov, then these equations can be applied within the limit they've been derived for. So they are actually accurate. We are not breaking any assumption in applying these equations. And again, we have been using the same DNS-based approach. We consider our fibers to be dispersed in the dilute regime, and we have been running some simulations. This is the shear Reynolds number of the flow. It's not very high, but the flow is fully turbulent. What we have been doing is change the inertia of the fibers by changing the Stokes number, and we have also considered different aspect ratios, which is the ratio of the major axis over the minor axis of the fiber, in order to investigate shape effects. So here in the last row of the table, I report the ratio of the length of the fiber. So this is the total length of the fiber when the fiber is fully stretched over the Kolmogorov length scale. And so you can see that our fibers are 3 to 7 times longer than Kolmogorov, whereas each segment is smaller or at most equal to the Kolmogorov scale. And this is how we define the Stokes number in this case. Remember, each element is basically a rod, and therefore the Stokes number is the one we would compute for spheres times a function of the aspect ratio, which takes into account the non-sphericity of the particle. The Stokes number is referred to the segment. If you want to have an idea of what the Stokes number of the whole fiber would be, then you can multiply by more or less a factor of 2. And this is a close-up view of what our flexible fibers do when they are in a real region. So this is only a portion of our channel, and now this is a close-up view showing the type of behavior that our flexible fibers have, in particular when they are close to the wall. As you can imagine, the fibers will accumulate at the wall, and this is a sort of animation of this near wall accumulation. Now, this is showing you the whole channel. So this is the entire channel seen from above, if you want. So from the normal direction. And this is the actual length of our flexible fibers compared to the entire computational domain. So you can appreciate the zoom that we did before. This is the actual size of the fiber, so you can probably see nothing here. But perhaps you notice that there is a sort of correlation between the position of the fibers which are entrapped at the wall and the near wall distribution of the fluid velocity, which is the color map that you see. So in red, you see high streamwise fluid velocity regions. See, these are the so-called high-speed streaks. In blue, you can see the low streamwise fluid velocity regions, which are called low-speed streaks. And so you can probably notice, for instance, here that the fibers tend to accumulate in low-speed streaks. This is a feature that has been observed also in the case of spherical particles. So even if our particles are non-spherical and flexible, this kind of behavior is kept. And the reason is that for this specific case I'm showing you, inertia is still the main factor driving particle distribution and particle interaction with the flow. In terms of near wall accumulation, we can, of course, again, look at the concentration. So these two plots show the concentration of the fibers as a function of the wall distance. The concentration is normalized by the initial concentration of the fibers. So when this ratio is equal to 1, the fibers have kept the same concentration as the initial one. If the value is higher than 1, then concentration in a certain region has increased. Now, on the left here, I show you two cases for two different sets of fibers which have the same inertia, so same Stokes number, which is referred here to the segment of the fiber, and same aspect ratio of the segment. The only difference between the two sets is that one set is made of rigid fibers that cannot deform under turbulence. The other set is made of flexible fibers, so they can deform under the action of turbulence. So the two sets start from the same initial condition, same spatial distribution. One doesn't deform, the other deforms in time. And as you can see, in the case of rigid fibers, we have a higher peak, which is still in the viscous sublayer. So you see that this tendency of accumulation, accumulating to the wall is shared with the small spherical particles. However, the peak in the case of flexible fibers is smaller, and you can see also that to a certain extent, flexibility allows fibers to be captured in a very, very tiny region, more or less 1.5 wall units away from the wall. So these are really close to the wall. Clearly, on the right, you can see what happens if you change the inertia of these fibers. And so on the right, I'm comparing only flexible fiber sets. We are just keeping the aspect ratio fixed, and we are increasing the inertia of the fiber by increasing the Stokes number. And you see that for the case in which the Stokes number is low, we have a peak that is quite close to the wall. But as we increase the Stokes number, the peak tends to shift away from the wall. So, but still the qualitative features of the concentration profiles remain the same. And we have been exploring also particle deformation, of course, not just their distribution inside the domain. And I will, for the sake of time, focus only on this result here, and I will skip the next slides in order to move to part 3. Now, what you see here is the PDF of this solid angle alpha. So what is alpha? Alpha is measuring the relative orientation of one segment in the fiber chain compared to the neighboring segment in the fiber chain. So if two neighboring segments are perfectly aligned in the three-dimensional space, then alpha is 0. So a fully stretched fiber in which all segments are perfectly aligned would have alpha equals 0 for all segment couples. Segment pairs, all right? If there is some relative orientation between neighboring segments, then alpha is not 0, all right? So what you see here is the ensemble average value of alpha, and the PDF is what is shown. Ensemble average is obtained by computing alpha for each segment pair in each fiber. Then we average alpha for a given fiber, and then we average over whole fibers that we consider. I hope it's clear. Now, in the plot, you see 4 different curves, 4 different PDFs. The red and the green refer to 2 different aspect ratios, lambda 2 and lambda 5 for the segment, and have been obtained considering only fibers in the near wall region. which we arbitrarily define as the region within 30 wall units from the wall. And the other two, the black and the blue, are the PDFs of the solid angle, which we measure for the same aspect ratios, but now considering only fibers that are instantaneously located in the bulk region of the flow, which is the remaining part of the domain. Now, what you see is that in this case, which refers to fibers with Stokes equal 30, so these are highly inertial fibers in our simulations, there is a clear peak of the PDF for values of alpha that are small or zero. So this is the case, remember, when all the segment pairs are more or less perfectly aligned. So that means that in this region, fibers are sort of stretched by turbulence. They are not deformed, they do not bend and coil. However, if we move in the bulk region of the flow, regardless of the aspect ratio that you can see here as a minor effect, the peak shifts towards higher values of alpha. So that indicates that in the center of the channel, the fibers are more deformed than near the wall. In this case, this is due to the fact that close to the wall, there is a strong and permanent shear produced by the change in velocity of the fluid, which is acting to stretch the fibers, right? This mean shear is not present in the bulk region of the flow, where turbulence is more, let's say, intermittent. So the fibers are, and each segment in the fiber is only subject to the instantaneous fluctuations, but there is no mean shear. And this is, in our opinion, what generates this different behavior. Again, for the sake of time, I will skip this plot because it's not adding too much to what I just said. So I hope that I have convinced you that by looking at this local interaction, we can understand some physics, which is not always so straightforward. Now, because it's already 42 minutes, let me skip this. These are just a few conclusions for this part. There are developments, of course, which have to do with the introduction of force coupling effects, which we have been neglecting. So there is no modulation of turbulence by fibers in the results I've showed you. Include full mechanical coupling, so not just force coupling, but also torque coupling. And that would allow us to study, for instance, the possibility of inducing drag reduction in the flow. Accounting for bending stiffness, so this was not included in our simulations. So the fibers, they just bend and deform freely, so to say, in response to turbulence. So there is no preferred conformation of the fiber in terms of energy, right? So any configuration, every type of deformation for the fibers is the same. And of course, it would be interesting to account for fiber-fiber collisions to investigate denser suspensions. But anyway, the idea was to start with something simple. Now let's move to part 3 quickly. So in this case, I would like to tell you a little bit about direct numerical simulation of particle droplet laden flow. So in this case, we have 3 phases, not 2 anymore. So in addition to the fluid and to the particles, we also have the deformable droplets that I mentioned to you before. And the long-term motivation for this study is the following. We want to investigate the change in the deformation of the drops that can be induced by particles that are trapped on the surface of the drops. So in this case, we have something analogous to what happens when the drops are laden with a surfactant. So if you put some surfactant on the interface on the surface of the drop, you will find a local change in the deformation of the drop. In particular, this is what happens in this case. So Of course, you will have some shear stresses, hydrodynamic shear stresses acting on the surface, which are represented here. These shear stresses will drive the surfactant and will produce a non-uniform concentration of surfactant. So for instance, this is the distribution on the drop that I'm showing to you. We will have regions of low surfactant concentration, which will correspond to high surface tension values, and regions of high surfactant concentration, which will correspond to locally low values of the surface tension. So you see that this produces a local difference in the deformability of the droplet. In the case of surfactant, this non-uniform concentration leads to the occurrence of additional stresses, additional to the shear ones, which are called the Marangoni stresses, which feedback on the shear stress one. But the main point is to take into account this effect of non-uniform concentration on surface tension. Typically, this is done by modifying the equation of state for the surface tension. This is the Langmuir, what is usually adopted is the Langmuir equation of state. So in the case of surfactant, you have tensors which are acting in the surface of the drop, which are called the Korteweg tensors. And these are inducing this non-uniform concentration that I told you before. These can be taken into account inside the equation of state, and then this equation of state can be used to change locally the Korteweg stresses, tensors. So this is the gradient of this tensor in the case of clean drop, and by using the equation of state, we can modify this term, which is a source term in the Navier-Stokes equation. What are we doing now is not yet look at the effect of the local concentration of particles, and so we are not yet considering changes in the distribution of the particles, but we are considering this simplified case in which we have turbulence, large droplets, and particles. And these are all the interactions that undergo among the three phases. So turbulence is deforming particles through the shear stresses, deforming droplets through the shear stresses, but droplets are in turn feedbacking on turbulence through the capillary stresses, so the Korteweg stresses that I mentioned before. Clearly also particles, which are just a little inertial, they are brought about by turbulence to the so-called turbophoresis, and in principle they could also exchange momentum with the fluid. If particles are interacting with droplets, they will respond to the local changes in the curvature of the droplets. And as I said, they might also induce local changes in surface tension. In what I'm going to present, and I will skip again a few slides, I will show you what happens if we neglect the momentum exchange between from the particles to the turbulence, and if we just consider a constant value of the surface tension. The methodology that we use is based again on an Euler-Lagrange approach. So we use a continuous approach for the carrier phase. This is the whole zoo of methods that you can use. And for the dispersed phases, in particular for the drops, we use the phase field method, which is an interface capturing method. And for the particles, we still use the Lagrangian particle tracking approach that I told you before. So for the carrier phase and for the drops, we solve for continuity and Navier-Stokes equation. We do direct numerical simulation of this equation, and this is the source term which accounts for the effect of the presence of the surface through the Korteweg stresses. As you can see here, these are not yet modified, and these equations are coupled with the Cahn-Hilliard equation, which is an equation that allows us to solve the time evolution of this phase indicator phi. So phi is equal to -1 inside the carrier fluid, is equal to +1 inside the droplet, and it's equal to 0 exactly at the interface between the fluid and the droplet. These are the assumptions that we have considered so far. So matched density between fluid and particles, matched viscosity, constant surface tension. For the Lagrangian particle tracking, we are considering the effect of the drag force and the capillary force. So this is the force by which the interface is able to attract the particle, to keep the particle actually on the surface. So this force here works this way. So I'm not going again into detail. So whenever a particle touches the interface, it is subject to the action of this capillary force. Actually, the force is activated whenever the particle crosses the surface for the first time. So the particle has to cross the surface for the first time. So in our model, it is considered as captured. And then the force acts always to retain the particle at the surface. So if the particle wants to escape, this force is trying to keep the particle on the surface and not letting it escape. The particle may escape if a strong turbulent event is occurring. And these are the conditions that we have considered for our simulations. In particular, we are considering different values of the Weber number. In this case, Weber is representing the change in the formability of the particle. And we are also considering different values of the Stokes number. But the Stokes number is kind of low in all the sets. So our particles are always weakly inertial. Now, I will show you maybe a couple of more slides to, again, tell you what kind of physical knowledge we can learn from these simulations, because I see that I already took too much of your time. Now, about particle capture, what we observe is that particles are captured in specific regions of the surface of the drop. So by looking really at the particle scale, what we observe is that the particles are typically led towards and brought towards the surface of the drop by sort of coherent, local coherent jets of fluid, which are impinging on the surface of the drop. So the particles just following these jets, and they reach the surface. Once they are there, they are retained at the surface through the capillary force that the surface can exert. And as you can see from this zoom in, so these are just a bunch of droplets inside our flow. As you can see, once they are trapped at the surface, they tend to move away from these regions. And they tend to disperse on the surface of the drop. You can see that clearly our droplets can deform a lot under the action of turbulence, and this has an effect on the distribution that the particles can attain. Let me skip this one. Now, in order to investigate the trapping process, so what happens to the particle once it has been captured, we decided that it was necessary to include what we called the excluded volume effects. So particles, in the simplest approach that I mentioned, in the absence of any collision, for instance, they can overlap. They are allowed to overlap. If you do nothing in your model, they can overlap and they can occupy the same region in the domain. In our case, therefore, if we don't include particle collisions, so if we do not prevent particles from overlapping, then we can find very, very densely concentrated clusters that have a form of a filament, as you can see here, all right, that are actually not physically plausible. Instead, if we include collisions, so if we include excluded volume effects, so particles must not occupy the same region in the flow and in particular on the surface, then we find still clusters more or less in the same regions of the drop, but clearly these are more smeared out. So they are going to occupy a wider portion of the surface. Now, this has clearly an effect, and I would like to actually move to the last slide, and then I'll finish. Because in this case, what you see here is a PDF of the curvature that is sampled by the particles that are trapped on the surface of the drop. All right, so this K at P is the curvature of the drop interface sampled by a trapped particle. And here we are normalizing this curvature by its mean value. All right, so in this plot, values of this ratio larger than 1 means curvature higher than the mean, smaller than 1 means curvature smaller than the mean. And clearly positive or negative values relate to concave or convex regions on the surface. Now, let's look at the main plot. So this is the PDF of this curvature in red for the case in which no excluded volume effects have been accounted for, so there are no collisions, particles can overlap. You can see that in this simplified but yet non-physical case, there is a clear peak of the PDF for values of the normalized curvature equal to about 2. So these particles tend to form clusters in regions where curvature is positive and generally higher than the mean. And the PDF is narrower. If we include excluded volume effect, we get the blue PDF, which has a lower peak that shifts towards the value 1, but most of all is broader. So you see that including excluded volume effects, and so imposing particles to occupy a wider portion of the surface, we see that now particle samples sample more preferentially than before regions of lower and negative curvature, but also regions of high positive curvature, so the highly convex and highly concave regions of the surface. That means that all these regions will be likely to be affected in terms of local surface tension value and so local deformability. So now that we can understand this kind of effect of what we think it's a realistic distribution of particles, then we can understand how the equation of state that I mentioned before can be modified for the case of particles. We know how to do it for the case of surfactant. We are still investigating how to do it for the case of particles. So with the conclusions for part 3, I thank you very much for your attention. I'm sorry for taking a lot of time, but I was expecting this because I know myself, so apologies for that. And if you have any questions, I will be happy to answer. So thanks a lot.
Great. So thank you so much for your talk, Cristian. That was fantastic. I know I learned a lot about I know I learned a lot about the particle interaction, so that was fantastic. Yeah, we do have time for questions. If you're in the audience, you can put your hand up and I can call on you, or just feel free to either type it in the chat or just unmute your mic and ask away. Maybe while people are kind of gathering their thoughts, I might ask one. This is just thinking about probably like part 2 of your talk, where you have the fibers, like just in terms of computational expense, how computationally expensive is it to have, I don't know, like 1,000 particles?
It's much more expensive than you know, the case of spherical particles. Clearly, even if the Reynolds number was not very high, we had to track individually many individual elements. In this case, the results I showed you include a total of 1.4 million of elements. And so you have to solve for all the equations for translation, rotation, and also connectivity constraints, which are a big part of the computational cost for all these segments for a very long time, let's say. There are also some issues if you want to use parallel computing for these kind of simulations, because you can imagine that we have this chain of segments or elements that can actually occupy different grid cells. Because the whole chain is several times the Kolmogorov scale. So in terms of exchange of information between the different processors that do the computation, you need to take this into account because at some point we cannot let's say put the entire flow field on one processor, and therefore it can just track every fiber individually. So let's say all of this is increasing a lot the computational time, and of course it depends a lot on the availability of processors that you had. But I would say that compared to a standard calculation with spherical particles, there is about 1 order of magnitude increase in the computational cost because of all these technical issues that you have to take into account. And clearly, I'm just talking about one-way coupling, and with two-way coupling, it's even worse. And with collisions, well, we haven't done yet this, but there are some papers in which both rigid and flexible fibers have been computed with collisions, and the cost is sort of exploding. So it's tough simulations.
Yeah, no, they're just really impressive. I mean, they're already impressive, so adding in the extra components is another step entirely. All right, any questions from the audience?
I took all the time, so people have stuff to do now.
No. Yeah, quite interesting talk. One question is that I wonder if we can relate your work with some COVID-related research, because somebody sneezes, it will produce a lot of the droplets.
Yes. Well, maybe not. I would say that the work I presented can be related. Clearly, the flow configuration is not the best suited for COVID applications, because, of course, there has been an explosion of works, mostly numerical, on the dispersion of these aerosols, which bring the virus inside, right? And most of the times, the flow configuration is a turbulent jet, which is replicating, like coughing, person coughing or speaking or shouting, whatever. But in this case, let's say the important feature which is missing in what I presented is of course the evaporation of these small aerosol drops. So clearly, what we could do for these three-phase simulations is to assume that our drops are replicating the aerosol, and our little particles, which would be actually much smaller than the ones we are considering, could be representing these small, the virus load, so the small virus laden case. As far as I know, there is a lot of work going on in improving the evaporation law, which is the D-square law that you probably know. And based on this law, so the diameter of this aerosol evolves in time as the square root of the initial diameter square minus a constant times time. This is not very accurate, and I know also some colleagues here in Italy, and even Professor Soldati, they are doing a lot of work, both computationally and experimentally, in order to improve the evaporation law. Because if you use the d-square law, then you can come up with this indication that within 7 feet or 6 feet or whatever, that's enough as a physical distancing for limiting the dispersion of virus. But in fact, the modifications to this law seem to indicate that the actual distance should be much more than what we know. And the other point is to understand the role of these airborne aerosols. So once the droplets, the respiratory droplets have completed their evaporation process, you have these aerosols which remain airborne, and they can be there forever in a room. From the fluid mechanics point of view, I think this can be done even with our code. We should change the geometry, the flow geometry. But I think that in order to do something meaningful, we need also the expertise of biologists and doctors, because I have no idea of, you know, what happens or what is the viral load of you know, COVID inside these aerosol. Is it relevant? Is it not? So yeah, of course, there is a lot to do. I didn't do it because I didn't think that I was able to produce something meaningful, so I didn't want to just produce yet another simulation. But you know, I think that a lot can be done also from the modeling point of view, because all of these evaporation laws are very old. I mean, I was surprised to know when and how these were obtained almost 100 years ago. And clearly, if an experiment was run 100 years ago, for instance, how could the scientist detect 1 micron or 2 micron or 5 micron small drops being ejected by, you know, a coughing or something? So yeah, there is a lot to do. Yeah.
Yeah, thanks. Yeah, many knowledge would be necessary, and it seems that your work is very important.
I see that there is one question in the chat.
Yep.
Yep.
Yes. So maybe I can read it myself, right?
Yeah,
so,
go ahead.
From Tony, I'm wondering if there is much experimental work on rod-like fibers in turbulence towards at least some qualitative agreement with your find. Yeah. Yes. So there is a lot actually of experimental work, both with rigid fibers, a little less with flexible fibers. So in fact, I presented to you 2 cases, the flexible fibers one and the 3-phase flow, that are missing some experimental validation in a way. Of course, if you ask me, I trust my results because, you know, it's DNS. So from the point of view of the fluid, it's fine. And the equations that we use are used within the limits of application. So I trust that. But in terms of fibers, I have, and I didn't show these results, I have some validation with experimental results with rigid fibers in an open channel. These are experiments that were run, for instance, at KTH in Sweden, the Royal Institute of Technology in Stockholm, in which they were studying the formation of streaks of fibers in an open channel. In this case, the fibers are heavier than the fluid, which is water. So not the density ratios that we have been considering, something smaller, let's say, but still enough for the fibers to be able to sediment and deposit near the wall. And for the case of the rigid fibers, the streaks that are formed can be replicated in our simulations, even with the point particle approach, because remember, everything starts from this approach. In terms of simulations, there are also simulations in which the particles are, so the fibers are fully resolved. And therefore, I regard these as experiments. And again, from KTH. And these simulations show features that we are able to replicate with our fibers. For instance, if the fiber is long enough, instead of forming streaks that correlate with the low-speed streaks of fluid, the fibers are sampling the high-speed regions near the wall. This is what the fully resolved simulation show. And we are able to capture, at least qualitatively, this result by imposing long enough fibers. Clearly, in that case, we are somehow breaking the assumptions of the point particle, but still what we can find is that the fiber is brought to the wall by these vortices that I mentioned, but because of its length, it cannot move towards the low-speed regions. It is always brought to the wall in the high-speed regions, but if it's short, it can move sideways towards the low-speed regions. This is what spherical particles do, in fact. If it's too long, it cannot do that because it cannot go too much inside the viscous sublayer, and therefore it is able to leave the near-wall region rather soon. So it is missing this kind of interaction with the viscous sublayer structures. And this is obtained explicitly in the fully resolved simulation, but somehow we can get that also with our simulations. Clearly, we have to stick to the qualitative comparison. I'm not claiming that the results I showed you are quantitative perfect. Trends are fine. I think we can understand what happens if you change one parameter or the other. That's what we can get from these results. So I hope I have read. I can give you more details if you're interested later on with all the papers. Of course, that is limited to dilute suspensions, because if you think of more dense suspension in which you have collisions, then collision, you see, they are changing things also from a physical point of view. So the interaction is really different in that case.
I have a question.
Mohammed, is that you?
Muhammad, yeah.
Mohammed, yeah, sorry.
No worries. These flexible fibers that you are using,
yes.
This accumulation near the wall and the interaction with the viscous sublayer and near the wall region, does it affect the drag of the turbulent flow, like make drag reduction like polymers?
Yeah, that's what we think, but it was not included in the simulations yet. But the idea was, yes, to explore this effect. So for the simulations I showed you, the number of fibers is not large enough to induce locally high mass fractions. So I think that, well, we have verified that, in fact, that including a two-way coupling, so including the momentum exchange from the particles to the turbulence, would not modify turbulence that much in our case. But in general, the motivation for looking at this problem was, in fact, the long-term one, of course, was in fact to include this momentum exchange, also to couple the torques and include bending stiffness. So these are the future developments that I just hinted to. Because if we include these effects, then I think that we can really understand how the modulation of turbulence is produced by these fibers. So I cannot, let's say, show you results, but for sure that's an important effect. And I would say that this bending stiffness, so the fact that the fiber can resist to any bending deformation induced by turbulence, this would be an important addition to our model. More than two-way coupling or another type of coupling. I think that the bending stiffness is what I believe the important
it's like the elasticity
to add.
It's like the elasticity of the polymer itself.
Yeah. In fact, yes. you know, the explanation of drag reduction induced by polymers, the one that I think it's let's say convincing to me at least, is that again the polymer chain has to be stretched by turbulence, so the energy goes into you know, the stretching of the polymer. And I think that is why you see that polymers are much more effective in producing drag reduction, because this is the effect you want, when they are close to the near wall region of a pipe or a channel, because it's in that region where this stretching can occur. If your polymers stay in the bulk of the flow, you will not see any drag reduction, right? So in our view, our fibers will do the same, but of course, unfortunately, I don't have the results yet, but we are working on that.
Okay, thank you.
All right, any last minute questions before we finish up? Last chance. All right, otherwise we'll thank our speaker one more time. Thank you, Cristian, for your excellent talk, and hopefully see our audience next week. So thanks again.